In this video, I am going to solve the numerical problems for chapter 13, Vibrations and Waves. First question. What is the magnitude of pulling force that is required to pull a spring with a spring constant K equal to 20 Newton per meter for a distance of x is equal to 25 centimeter? So for finding the value of the pulling force, we have to use the Hooke's law. So here the spring constant value is given, which is K equal to 20 Newton per meter, and the extension of the spring here is given, which is 25 centimeter, and its related figure is given here. So you will get all the information from this figure, right? Okay, now I have to convert this 25 centimeter in terms of meter. Therefore 25 multiplied by 10 power minus 2 will give the answer in terms of meter. Now what I am going to do, I am going to apply the Hooke's law. The Hooke's law is given by the relation F, which is equal to minus Kx. And here we are going to find only the magnitude of the force. So therefore the magnitude of the force, which is given by the relation Kx. Now I am going to substitute the value for K as well as for X. So by that, this equation, after substituting the value here, this equation will become K equal to 20 Newton per meter multiply with 25 multiply with 10 power minus 2. So now I'm going to multiply these two for getting the value of the pulling force. So let's wait. So 20 multiplied with 25 10 power minus 2, I got the answer as 5 Newton. And this is the answer for this question. Clear? Second question. Calculate the elastic potential energy stored in the spring when the spring is stretched from 7 centimeter to 15 centimeter. So here the initial value of the extension as well as the final value of the extension is given here. So by that we can easily find the value of x, right? So I am going to find the value of the spring, that is x, which is equal to x final minus x initial. So the value of x final here is 15 centimeter minus 7 centimeter. So 15 minus 7 gives the answer of 8 centimeter. So that is the value of the extension of the spring here. So therefore x, which is equal to 8 multiplied by 10 power minus 2 meter. And the spring constant value for the spring here is given as K equal to 50 Newton per meter. Now we are going to find the elastic potential energy, which is given by the relation potential energy, which is elastic potential energy equal to half K x square. This is the rule, right? So now I am going to substitute the value of the K here, and I am going to substitute the value of x here. So by that you will get the answer for the elastic potential energy. So after I substitute the value in this equation, the equation will become half multiplied by the K will take 50 Newton per meter, and the x value is nothing but 8 multiplied by 10 power minus 2 the whole square. So 8 multiplied 10 power minus 2 the whole square. So I have to multiply and divide with 2. So we have to wait for the answer. 50 multiplied by 8 10 power minus 2 the whole square divided by 2. I got the answer as 0.16. So the elastic potential energy value here is 0.16 and its unit is joule. Clear? So this is the answer for this question. Third question. A 0.4 kilogram block with an initial velocity of Vi equal to 2 meter per second collide with a spring that has the spring constant of 25 Newton per meter. Calculate the maximum compression resulted from the collision. So what they gave in the question, you have to see the figure. You have the block of mass which has the value of 0.4 kilogram, which is coming with the initial velocity of 2 meter per second. And it is going to hit the spring. So before collision, the block had this velocity, but after collision, what happened? The velocity of the blocks becomes 0. So here, before collision, it has the initial velocity Vi, which is equal to 2 meter per second, and the mass of the block here they mention as 0.4 kilogram, and we are going to find after the collision takes place the spring will compress. By that the final speed of the block becomes 0. Clear? And now what we are going to do, we are going to find what should be the value of the compressed level of the spring. We are going to find the value of x. Clear? Okay, now for getting the value of this, we need the spring constant, and that value is already given here, which is 25 Newton per meter. So for getting the value of the compressed value of the x, we have to use the law of conservation of mechanical energy for this case. So as we already know, in many questions, we are using this law of conservation of mechanical energy. So likewise, we have to apply the law of conservation of energy for this category. So we know the kinetic energy initial plus potential energy initial, which is equal to the kinetic energy final plus potential energy final. Now you have to see this potential energy. This potential energy is not a gravitational potential energy, because here the block is moving in the horizontal, right? So there is no altitude, there is no height related to this part. So the gravitational potential energy will not be applicable for this case. So here the potential energy, what I mentioned here, is nothing but the elastic potential energy. So now if you want to know the formula for the kinetic energy as well as the elastic potential energy, the kinetic energy rule is half mv square plus half kxi square, which is equal to half mvf square plus half kxf square. Now if you see here, initially this block will have the speed, but the spring will not compress. So initial compression value of the spring we are not going to consider. But after the collision takes place, what will happen? The block speed becomes 0, but the spring is compressed. That means we are going to consider the final speed of the block is 0. So anything multiplied by 0 is 0, but finally you will get only the answer for this final elastic potential energy. Now I am going to use this part, that is half mvi square, which is equal to half k xf square. Here xf is nothing but the compressed value of the spring. And now we can cancel this half both left hand side and the right hand side, and by that we can easily rearrange this part in terms of xf, because we are going to find the value of the compressed value of the spring. So by that, if you rearrange, what will happen? Xf square, which is equal to mvi square over k, right? And we have all the values here. The mass of the block they mentioned here as, and here this value is nothing but the square, right? So if you take the square both left hand side and the right hand side, you will get the value of xf, right? So I'm going to take square root on both left hand side and the right hand side. By that, this equation will become xf, which is xf, which is equal to square root of, I'm going to substitute the value here. Therefore, xf, which is equal to square root of, the mass value here is 0.4 multiplied with the initial speed of the block is 2 meter per second. So it is 2 square over the value of the spring constant here is 25. So now I have to calculate for getting the value of xf. Square root of 0.4 multiplied with 2 square over 25. So I got the answer as 0.253. What's the answer? 0.253, and its unit is meter. So this is the answer for this question. Clear? Question number 4. A 2 kilogram block or object on a frictionless horizontal surface is attached to one end of the horizontal spring of force constant K equal to 4.5 kilonewton per meter. The other end of the spring is held stationary. The spring is stretched 10 centimeter from equilibrium and released. So what they gave in the question, you have to see the figure. You have the horizontal frictionless surface, and you have the spring. One end of the spring is connected to the wall, and another end of the spring is connected with the block of mass, and you extended the spring to the maximum value of 10 centimeter. And its K value is given as 4.5 kilonewton. So we have to multiply 4.5 with 10 power 3. And by using this, we are going to find what is the total mechanical energy. So total mechanical energy, which is equal to the kinetic energy plus potential energy. So here the block is under rest. So the potential, the kinetic energy is 0. The only you have the value of the elastic potential energy, and even this is not an elastic potential energy because you are extending the block to a maximum value of 10 centimeter. So by that we can write the mechanical energy, which is equal to half k a square. So why I just write a square in place of x square? Because we extended the block to the maximum value of 10 centimeter. So that is nothing but here they mention the amplitude. The maximum exerted from the equilibrium condition is considered to be an amplitude. So here in place of x square, because we have one more x value, so I have to differentiate these two. So now what I'm going to do, I'm going to substitute the value here. So here the value of A is nothing but 10 centimeter, and the K value here they mention as 4.5 kilo Newton per meter. Now I'm going to substitute the value, therefore half multiply with the K value is 4.5 multiply by 10 power 3 multiply with the amplitude 10 multiplied by 10 power minus 2 the whole square. It's not 3, it's minus 2 the whole square. So I have to multiply the numerator and divide with 2. So by that I got the total mechanical energy as 22.5 joule. So this is the answer for the first part. Clear? Now we have to move the second part. What is given in the second part? The velocity of the object at equilibrium position x is equal to 0. So for the position of x is equal to 0, we are going to find what should be the value of the maximum speed. So for that, I have to use the mechanical energy rule, which is half k a square, which is equal to half m v square. So for this part of the left hand side, I'm going to use the value of 22.5, and by that we can easily find the value of the maximum speed or maximum velocity, right? So I have to rearrange this equation. Therefore v square, which is equal to 2 multiply, and for all this half k a square, which is nothing but our mechanical energy, right? All this half k a square is nothing but the mechanical energy. So for this part I am going to take 22.5, which we already calculated in the first part, right? So p square, which is equal to this 2 will come to this value. So 2 multiplied by 22.5 divided with the mass of the object, which is 2.4, right? Now I have to find, and after that I have to take the square root. So we take the square root here. Therefore the above equation, if you take the square root, what will happen? This value become 2 multiplied with square root of 2 multiplied with 22.5 over 2.4. So I have to calculate the value of the maximum speed. So square root of 2 multiplied by 22.5 over 2.4. I got the answer as 4.33 meter per second. 4.33 meter per second. So this is the answer for the maximum speed. In the third part, we are going to find what is its velocity and what is its kinetic energy, what is its potential energy. Here the potential energy is nothing but the elastic potential energy. As we already studied the relation for the velocity, we know the rule V, which is equal to square root of k over m multiplied with a square minus x square. So here the x value is given, and here a is nothing but the maximum extension value of the spring. So if you substitute the value, we have all the values here. We have the spring constant, we have the mass of the object, we have the maximum exerted. We are just moving the spring to 10 centimeter, which is nothing but the amplitude A, and also the x value is given here. So once I substitute the value here, I will easily find what is the velocity. Clear? So let's substitute square root of k value here is 4.5. It's kilonewton. So 10 power plus 3. So 4.5 multiply 10 power plus 3 over the mass of the object is 2.4 multiplied with the amplitude square is 10 multiplied by 10 power minus 2 the whole square minus the value of the x here is given as 7 centimeter. So 7 multiplied with 10 power minus 2 the square. I have to close the bracket. So now I have to calculate what should be the answer for this. Four 4.5 10 power 3 over 2.4. In the top I have to multiply with 10 multiply 10 power minus 2 the square minus 7 10 power minus 2 square. Close the bracket. I got the answer as minus 3.09 meter per second. Clear? And second one, we have to find the kinetic energy. So once you find the value of the velocity, we can easily find the kinetic energy. So the value of the formula for the kinetic energy is half mv square. So the v value, I'm going to take only the magnitude here. I'm going to substitute here. So half the mass value here is 2.4, and the velocity I'm going to take only the magnitude, which is 3.09 square. I have to calculate. I got the answer as 11.46 joules. And finally, I have to calculate the elastic potential energy, which is given by the rule half k x square. So here x is nothing but this value 7 centimeter. So I have to substitute the value here, half multiply with the k value is 4.5 multiply 10 power 3 multiply with the x value 7 centimeter. So 7 multiplied by 10 power minus 2 the whole square. So the answer I got is 11.03 joules. So this is the answer for the last question. Clear? Next question. The figure shows the x versus t graph of a simple harmonic motion of an object attached to the horizontal spring. Find the following. So here the diagram, the figure is given. By using the figure, now we are going to for the question. Clear? Okay, what is given in the figure? They give the graph which indicates x versus t. In y-axis they take the displacement value, in x-axis they took the time value. By using this, we are going to answer all these questions. First question, find the amplitude of the motion. What is the amplitude? We studied in the theory how much the wave will be exerted from the equilibrium condition. Here the equilibrium condition is 0, so it will be exerted from the equilibrium to 0.5 meter. So that is nothing but our amplitude. So therefore the amplitude A is equal to 0.5 meter. Now we have to answer for the time period. By using this wave diagram, we are going to find the time period. What is the definition for time period? The time taken for one complete oscillation to occur, which is nothing but the time period, right? So that means one complete oscillation. That means it starts with 0. So one complete wave, that means it is starting from here 0 and it will go to 2 and then it will come to 4. So this is nothing but one complete cycle. So for this one complete cycle, what's the time here? So the time period here is nothing but 4 seconds. So the answer for the second question, t, which is equal to 4 seconds. Clear? And third question, we are going to find the answer for the frequency. As we already solved one question, the frequency is nothing but it's the inverse of the time period. So therefore frequency, which is equal to 1 over time period. Therefore 1 over time period value I'm going to take from the B part, which is 4 seconds. So 1 over 4, which give the answer as 0.25 hertz or 1 over second. And finally, we are going to find the value of the angular frequency. We know the relation omega, which is equal to 2 pi f. So I'm going to take the value of the third part. I'm going to substitute here. So omega, which is equal to 2 multiplied by pi multiplied by the frequency. The frequency here is nothing but 0.25. So I'm going to substitute the value here. So if you multiply 2 pi with the 0.25, we got the answer as 1.57 and the unit is rad per second. Clear? So this is the answer for this question. A simple pendulum of length 0.7 meter executes a simple harmonic motion. So you have to see the figure. It's a figure for the simple pendulum. So the length of the pendulum here is given as 0.7 meter. So L, which is equal to 0.7 meter, I have to write it here. And we are going to find what is the period of the motion, and you have to use the value of the acceleration due to gravity g, which is equal to 9.8 meter per second square. Now we already studied the relation for the time period for the simple pendulum, which is given by the rule t equal to 2 pi multiply with square root of L over g. This is the relation we studied in the theory, right? Now I'm going to use this equation for finding the value of the time period. And I'm going to substitute the value of L as well as the value of the G. Once you substitute the value in this equation, you will get the answer for the time period, right? So therefore, the time period T, which is equal to 2 pi square root of, the L value here is 0.7 meter over the gravity value is 9.8. And if you just calculate this right hand side of this equation, we will get the answer as 1.68 seconds. So the answer for this question is 1.68 second. Clear? 8th question. It's a fill in the blanks, so we have to read carefully before you give the answer. So let's start with the first question. A motion is said to be a simple harmonic motion when the net force is directly proportional to the dash from the equilibrium position. So the net force is directly proportional to the displacement from the equilibrium position, right? So the answer here is displacement. Second question. The speed of an object attached to a spring undergoing simple harmonic motion is 0 when the spring displacement equals amplitude. The elastic potential energy for a spring that is at an equilibrium state, not stretched nor compressed, is 0. Right? Match the following. So you have to read and then you have to choose the correct answer here. The unit of the spring constant, what is the unit? The unit for the spring constant is Newton per meter. So the answer for the first question is here. The elastic potential energy of the spring is given by the relation half kx square, and that answer is here. So the answer for the second one is this one. And the unit for the frequency, we have two units for the frequency. One is hertz and second one is 1 over second. So here they give the unit as hertz. So the answer for the third question is hertz. Clear? That's it. Thank you.